everyone. Let's talk about dating. And I don't mean like it's swipe left or swipe right or whichever way you swipe kind. I mean, how do we find out how old fossils are when we find them in the fossil record? So when we find something like this, how do we know exactly how long ago it lived? Because what we want to do with those fossils when we find them is we want to use them to reconstruct our family tree, our evolutionary history. But it's important that we know exactly where that thing belongs because what we really find are just little snippets of this evolutionary history because of taphonomic processes that result in not everything becoming a fossil that ever lived and not finding every fossil that ever got fossilized. We just have these little bits and pieces of our evolutionary history that we want to know how to put together in a family tree. And it's important to know how old those little pieces are so that we know how to reconstruct that family tree. So we need dates so that we can make these using those fossils that look like this. So how do we know when these things lived? Well, we used geology, chemistry, and physics to figure this out. And there are some things that you really already intuitively understand. You intuitively understand the study of stratigraphy, which is the sequential layering of geological deposits. We'll call any one layer a stratum, that's the singular, and then strata are laid down on top of each other in depositional events like floods and rainstorms and dust storms and things like that, anything that deposits sediment on top of the ground. You also intuitively understand the principle of original horizontality. You understand that when a stratum is first laid down, it's laid down horizontally to the ground. You know this because you've made a cake before. So you know both that when you pour a layer of cake, it lays down horizontally across the bottom of the pan. And you also know that the things that are on the bottom are older than the things that are on the top. You know intuitively that the purple layer of this cake was put down first, and then there was a layer of icing that got put down, and then the blue layer got put down, and then there was another layer of icing. You know the order of events that happened here because you've made a cake before and you know how this works. You can also tell how old or young something is, even if the strata have been disturbed. So if you look at these sequences, you know intuitively that the strata on the left is older than the stratum on the right, unless this whole section got flipped completely over, which is fairly unlikely. It's much more likely that it just got lifted up on one side. So you understand that intuitively. You also understand that if you find something in this layer of the stratum, it's the same age as whatever is over here in this layer because this is part of the same stratum that got disturbed at some point after it was deposited. You also intuitively understand that whatever event caused the disturbance in these strata happened after the strata were laid down, because otherwise it wouldn't have disturbed those strata. So you understand a lot about this kind of dating, and it all relies on the principle of superposition, which says that younger things are on the top and older things are on the bottom. So you can use this when you find a fossil, and you can infer that this fossil in the top of the sequence is younger than this fossil at the bottom of the sequence. That's all based on the principle of superposition. But that's not very satisfying because that's what we call relative dating. You only know that something is older than or younger than something else. You don't know exactly how old it is. But we need to know how old things are. It's really much more useful to know exactly how old things are because you know a lot more about it that way. So we need what are called absolute dates. So we want absolute ages for things. And we get those absolute dates from special layers in the stratigraphy called tephra. These are layers that are caused when volcanoes explode and they deposit a lot of ash in a layer. And these layers have special properties. What we can use these layers for is to get absolute dates because we can use the principle of isotopic decay of some isotopes that are in these layers to age them, to figure out how long ago it was that that volcano exploded. The main ones that we use, they're not the only ones, but the main ones that we use are potassium and argon, and then argon and argon. So there's potassium in volcanic explosions, but when a volcano explodes, there's no argon left in the volcanic explosion because argon is a gas and it's driven off by the heat of the volcanic explosion. So once the layer of volcanic ash, the tuff, is deposited, potassium immediately starts decaying into argon. So potassium 40 decays into argon 40. And chemists and physicists have figured out exactly how fast this occurs. This is called a half-life. And so we use the half-life, the known rate at which potassium 40 decays into argon 40 to figure out how long it's been since we had 100% potassium. So I'm going to step you through a really simple mathematical example of how this works so that you can wrap your mind around it. So radioactive isotopes decay at a predictable rate. That's known as their half-life. And for one half-life, the definition of a half-life is that one half of the parent isotope, whatever that happens to be, will have decayed into the daughter isotope after one half-life. So let's do this with a really simple half-life of 1,000 years. So we don't have to pull out any calculators. So let's say that isotope Q decays into isotope Z with a half-life of 1,000 years. So we know that when volcanic explosions occur, 100% of whatever we have is the parent isotope. So that's isotope Q. After one half-life, half of the isotope Q that is present will have decayed into isotope Z. So what we're going to have after 1,000 years, in our case, is half Q and half Z. One half Q and one half Z. Now this next step is where it gets a little bit tricky and sometimes students get tripped up. So the definition of a half-life again is that after one half-life, half of the parent isotope that is there will decay into the daughter isotope. So in this case, half of this will decay into Z after another half-life. So that what we have after two half-lives is 2/8 or 1/4 Q and 6/8 or 3/4 Z. So this isotopic decay is not linear. After three half-lives, 3,000 years, what we'll have is 1/8 Q and 7/8 Z, because half of this remaining parent isotope will decay into the daughter isotope. And this continues and continues and continues, so that after 4,000 years, what we'll have is 1/16 Q and 15/16 Z. Then after 5,000 years, we'll have 1/32 Q and 31/32 Z. And then after 6,000 years, we'll have 1/64 Q and 63/64 Z. And after 7,000 years, we'll have 1/128 Q and 127/128 Z, and so on and so on and so forth. And this will continue until there's not a measurable amount of Q left. So at the very beginning of the process, there's usually not enough Z to measure. And at the very end of this process, there's usually not enough Q to measure. And that length of time, how long it takes to have a measurable amount of the daughter isotope and a measurable amount of the parent isotope, will determine how useful over what kind of time span you can use this particular parent-daughter isotope pair to figure out the ages of stuff. So here is a graph of the half-life of potassium-argon decay. So potassium 40 decays eventually into argon 40. So potassium 40 is decreasing in a sample as argon 40 is increasing in a sample. And the half-life of potassium-argon is 1.25 billion years. So we can actually use this to date things that are about 10,000 years old to older than the age of the Earth. Argon-argon dating works in the same way. Argon 40, as soon as it's made, or as soon as it appears as decay of potassium 40, immediately starts decaying into argon 39. So sometimes we use that isotope pair, parent-daughter isotope pair. Carbon 14 dating works in the same way, but carbon 14 has a much shorter half-life than potassium argon or argon argon. So it's useful to date things that are much, much younger. So we can't really use that to date anything that's about older than about 50,000 or 60,000 years. So that's useful in archaeological settings, but it's not that useful in paleoanthropological settings. So that's the basic premise of how all of this absolute dating works. There are other ways that we use to date things, but your book didn't explain very well exactly how radioisotope radioisotopic decay works and how we use it to figure out how old things are. So I wanted you to have a better explanation of that so that you weren't just accepting things that we say in the textbook, but you actually understand the evidence behind what we're telling you in the textbook. All right, I hope that clarifies.